this is APAB Calc. We're doing Intro to BC, which is ITBC, and we're doing topic number 1, which is parts. So in example 5, we're going to do parts when the dv involves some simple u sub. So using liat, right, we always use liat to choose our u, so liat. I see that the algebraic function, which is the x to the 4th, will be my u, and the exponential stuff and everything else that's left over will be my dv, right? Now, because this u would derive to 0 eventually, right? Eventually, x to the 4th is going to derive down to a constant, which will then derive to 0. I can use the shortcut, which is a good idea here because it would be a lot of rounds of parts if you were doing it without the shortcut. So let's go ahead and put my derive column. That's not how you spell derive. It's like I had one job and it involved spelling derive. Okay, so my derive column is going to start with an x to the 4th, and I need an integrate column that's going to start with an e to the 2x. Okay, so let's do the derivative first, right? So derivative of x to the 4th is going to be 4x cubed. Derivative of 4x cubed is going to be 12x squared. Derivative of 12x squared is going to be 24x. Derivative of 24x is 24. And then finally 0, right? And that's where I stop. I go down until I hit 0. Okay, so now here's the part where the whole reason I mentioned this whole dv needs simple u sub. So if you were to integrate e to the 2x, every time you, well, let's start with if you were deriving e to the 2x. Because of the chain rule, if you were to derive e to the 2x, every time you derive, you'd end up multiplying by 2. Similarly, if you're integrating e to the 2x, every time you integrate, because of that sort of reverse chain rule, you'd have to divide by 2. That's essentially simple u sub, but it's a lot easier if you can spot the pattern. So when I integrate, I'm going to get a 1/2 e to the 2x. When I integrate again, I'm going to get a 1/4 e to the 2x. When I integrate again, I'll get a 1/8 e to the 2x. When I integrate again, I'll get a 1/16 e to the 2x. And when I integrate one more time, I'm going to get a 1/32 e to the 2x, right? I'm just going to do a quick double check that I did go straight across. Sometimes the fractions get me a little messed up. Okay, cool. So now I'm going to go ahead and use my shortcut, right? So from the x to the 4th down to the 1/2 e to the x, that's going to be positive, right? So I'm going to have an x to the 4th over 2 e to the 2x, right? That's my positive term, right? Then from the 4x cubed down to the 1/4 e to the x, that's going to be negative, right? So I'm going to get minus, well, the 4 over 4 is just a 1, so I get an x cubed e to the 2x, right? Then from the 12x squared down to the 1/8, I'm going to get a positive, right? So 12 over 8 should be 3 over 2, right? So I get plus 3 over 2 x squared e to the 2x, right? Then from the 24x down to the 1/16, 24 over a 16th, I'm going to be able to cancel 8s, so I get another 3 over 2, but this one's going to be a minus because we're alternating signs, so minus a 3/2 x e to the 2x, right? And then the 24 to the 1/32nd should be my last entry because anything below that will be a 0. So I'm going to get a plus 24 over 32. They both have 8s, so that should be 3/4 e to the 2x, and then, of course, tack on the plus c. So my final answer, if I go ahead and write that as one giant line of stuff, which we'll do up here, right? So if I try and squeeze this all into one giant line of stuff, I get an x to the 4th over 2 e to the 2x minus an x cubed e to the 2x plus a 3/2 x squared e to the 2x minus a 3/2 x e to the 2x plus a 3/4 e to the 2x plus c. So again, without the shortcut, this would be somewhat unbearable, right? Like this is not one you want to do without the shortcut. That's a pretty lengthy problem, okay?